Assalamualaikum warahmatullahi wabarakatuh. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam, Doktor.
So, sound clear? Is it my sound clear? Sister, brother?
Yes, Doctor. Yes, Doctor.
Because I just want to check whether it's not clear or not, because I use this earphone, but when I open my mic, but there could not listen my voice, so I'm worried. Okay, so good then. So we are continuing regarding with the semiconductor devices. So today we would like to explore more regarding with the PN junction. Yeah, so we have two kind of material, P semiconductor and N semiconductor. Yeah, P semiconductor means many excess of holes, yeah, in the semiconductor matrix. And N type of semiconductor, there are many excess of electron, yeah, in the semiconductor. So as like in previous illustration, so I draw the okay, so we have a PN junction. If we have a just recall, yeah, last week, okay, I make it more clear. We have a P and we have a N. Yeah. So P means that we have many excess of holes, meaning that we have a doping of like a boron. That boron only supply 3 electrons to be shared. So meaning that the less one of electron, yeah, to be shared to the silicon matrix. So meaning that there we have a hole, yeah, one hole, excess of hole. So hole represent the positive charge, yeah. And then we have another side. We have a excess of electron. Yeah, in the silicon matrix we have like a atom of phosphorus. So we have one excess of electron of phosphorus that cannot be shared. So then the electron will be the position close to the conduction band. Yeah. So what happened with this connection between the P and N? Yeah, as we have discussed last week, that the electron will diffuse to the P, yeah, and then the recombine with the hole. On the other hand, hole also moving, yeah, to the N region. So this kind of moving of electron, yeah, so we call as a diffusion, yeah, diffusion. Diffusion of electron and diffusion of holes. So in this case, the diffusion of electron and diffusion of hole will not go further, yeah, to the for example, all of hole will not go to the electron here, yeah, recombine with all of electron in the N type, but or all of electrons in the N type will not go to the P type hole, yeah. All of these will not go. So only we have in the region here. So then we can call as a depletion region. Yeah. Okay, so the diffusion of electron and holes in here, they will generate, yeah, the potential difference. Yeah, so here will be many yeah, piece of hole moving here, so this will be positive, yeah, more positive, and here will more negative. Yeah, so the uh, uh, because of this diffusion, so will generate, yeah, will generate the potential difference between in the p region and the n region. So we have a potential difference. Yeah, this is a positive and this negative. So, and then the potential difference will generate the electric field E. Yeah, so this electric field caused by the diffusivity of the electron and holes, yeah, will causing potential difference and electric field. The electric field further, yeah, will attract. Yeah, so this is a positive and the negative. So the positive will attract the electron from P again. Yeah, and then the positive charge will be moved here to the P, yeah, from N. So this the moving of electron, yeah. So this is we call as a, for example, the electron from the P, yeah, to the right. So we have called as a drift. Yeah, the drift of electron from P to the N because of the diffusion, yeah, of the electron and hole, and generate the potential difference. And potential difference will cause the electric field. So the electric field will causing the mobility, yeah, of the electron to the n type and the hole from n type to the p type. Yeah. So this is the drift of a electron, or drift of hole. Yeah, drift of electron go to the right, and this is drift of electron, and the drift of hole, yeah, uh, hole go to the left. Yeah. So uh, then, yeah, the moving of electron. The moving of electron, as we have discussed last time, the moving electron can cause the uh, current, right? Usually, the electric current. The electric current is illustrated by the moving of a positive charge. The positive charge here can be represented by the hole, yeah, the moving of hole. So, in this case, we have the current, yeah, yeah, of diffusion, yeah, by the diffusion, yeah, current of diffusion. Where's the direction of the diffusion current? To the left or to the right? Siapa boleh jawab? Brother, sister, diffusion current will be to the left or to the right? Hmm?
To the right.
To the right. Yeah, correct. Because this is considered the moving of hole. So the diffusion of hole. Yeah, so this is as a electric current of diffusion. Then we have what? Diffusion of drift. Diffusion of drift is a moving of a hole or positive charge from the right to the left. So they oppositely. So this is the current, diffusion current and the drift current. Yeah, is considered to be same. Yeah, because only in this area, in this area, to the left, to the right, to the left, to the right. Yeah, a hole to the right and causing the electric field causing the attraction of electron to the right. So this is only in this region. Yeah, so in this depletion region. So in this case, yeah, since there is no any other, yeah, external energy, yeah, we do not have external energy. Yeah, this is open. Yeah, so therefore the diffusion of current and drift current should be same. So this is a same, yeah, diffusion current and diffusion drift current, yeah, and PN junction, yeah, only in the contact junction, yeah. So then from this, so we can from the diffusion is because of the electron and hole have a diffusivity, and the drift current because of the there is the mobility of the electron and hole, yeah, because of the because of under the electric field here, yeah, then the electron moving to the right, yeah, and the positive charge to the left, yeah, because of there is the mobility. So this is the property, yeah, of the materials, yeah. Silicon, for example, will be different, yeah, diffusivity, electron or hole in germanium, yeah, and germanium and silicon will be different, yeah. Okay, so this like the illustration, this is a diffusivity, yeah. We have a silicon, right? Silicon and diffusivity of electron dn, yeah, square centimeter per second, 35, yeah, 35. Diffusivity of holes, square centimeter per second, 12.5, yeah. So diffusivity of electron will be faster, yeah. And then mobility, because under the electric field generated by the diffusivity, yeah, so then the mobility of electron, yeah, cubic yeah, centimeter yeah, per volume second, yeah. This is also for the mobility of a hole, yeah, centimeter square, yeah, per volt second. So this is the we can understand, yeah. So actually later, yeah, we will analyze, yeah, when the this is N and this is P, yeah. So when we consider diffusivity, so that the diffusivity of a electron will be faster, yeah. So we can understand, yeah, logically, and then the diffusivity of electron, yeah, until here, yeah, yeah, in this area, yeah, until this location. But the hole only in this area. So this is will be different, yeah, widths, yeah. Uh, yeah, the x will be different, yeah. Mobility of diffusivity of electron, yeah, will be further, yeah, of longer than diffusivity of a hole, yeah. So from this we understand, and then will be different for germanium, yeah, we see, and from for gallium arsenide also different. Okay. Now let's see the illustration further about the PN junction. So this is we have a P and we have N, and we have the energy band, yeah, energy band for the P type semiconductor, yeah. This is a valence band and this is a conduction band, yeah. And then the Fermi surface, or the excess of hole location is close to the valence band, yeah. So this is a Fermi surface, yeah. We understand from the solid state physics, yeah, the Fermi surface is where the electron moving, yeah, or partially occupied orbital, yeah, molecular orbital, or half, yeah, or empty. Yeah. So this is uh, the level of the Fermi surface, yeah, for a certain dopant, yeah, phosphorus, yeah, and other different dopant, yeah, that causing the excess of holes. So the position will be different, yeah, yeah. So we have seen last time, yeah, for the phosphorus, the energy band and energy level, Fermi level, it will be 0. Yeah, 0.045 electron volt. Yeah. And N type of semiconductor, we have the Fermi surface close to the conduction band. Yeah, this is for example, dopant is phosphorus. Yeah, so this is the location of Fermi surface is close to the conduction band. Yeah, also you have maybe already performing the experiment. Yeah, experiment. Advanced materials experiment that you will draw or will simulate where is the Fermi surface. Okay, the Fermi surface is illustrated by so-called the reciprocal of the crystal structure. Okay, now what happened when we join together? When we join together, so there is the depletion region with the width W. Yeah, yeah. And then from this is the X. Yeah, this is the X direction, so showing the moving of the hole to the right and the electron to the left. Yeah, negative. And then uh, we have the potential difference. Yeah, when in equilibrium the potential difference causing the electric field. Yeah, so this is uh, the difference between uh, uh, P type and N type. So the different potential difference is a V0, yeah, and equilibrium. So we can call as a electrostatic potential, or we can call as a contact potential, yeah, contact potential or electrostatic potential, yeah, V0. And then what is the energy? Yeah, because potential V0 will cause the energy. The energy, of course, will be Q times the V0. Yeah, so this is the energy, or we can call as the electron volt. Okay, so this is the different energy between N type and P type. Yeah, there is the energy difference. Okay, sorry, we continue. There is the potential difference, and then the potential difference will cause the electric field. Yeah, and the electric field, of course, the is a can cause the mobility of electron and mobility of hole. So this part of the unit of the energy. So the energy is a Q V0. Yeah, the Q V0 actually the illustration, the different energy between the P and N type. Okay, so this is the energy level when we contact each other. Yeah, between P and N, so they will the Fermi surface will be the same location. Yeah, so this is the Fermi surface, this one, and then the this showing the different the energy between conduction. Sorry, between the P type and N type semiconductor. Okay, when they join together in equilibrium. Yeah, in equilibrium, yeah, this there is the potential difference, or we call as a contact potential, or we call as a electrostatic potential. Yeah, and the other term used, yeah, in other reference. So in this case, the drift current and the diffusion current should be 0, yeah, because the uh, 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 diffusion current, yeah, to the right, and the drift current to the left, yeah. So at the same, because it's in equilibrium, yeah. So there is no any external energy. So where there is no external energy, then we will be uh, 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 mobility of electron and diffusion of the electron will be same but different in direction. Let's see in detail, yeah, about the drift current and the diffusion current. Yeah, they will be 0. Yeah, and then the electric field here, yeah, the electric field, yeah, will causing the mobility, yeah, of the uh, uh, hole, yeah, positive charge, yeah, yeah, to the right, for example. And then diffusion, yeah, will be diffusivity, yeah, will be causing the penetration of the hole to the n type, yeah. So this is a we have again illustration. So this is P and this is N, yeah. And then the mobility, yeah, mobility is the mobility of a hole, this is from the right to the left. So this is a P, yeah, and the mobility, yeah, mobility, yeah. But diffusivity, yeah, hole, this because from the left to the right, yeah. So this is the causing the penetration of hole to the uh, n type, and then causing the uh, diffusion current, yeah. So this is a diffusion current, yeah? diffusion of a hole, yeah. Yeah. So this is the illustration, and then the uh, 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 this the summation of between the drift and diffusion current will be 0, yeah, or because of the different directions, so will be negative. Okay, and then we rearrange about the diffusion and the mobility to the electric field, so we can have this equation. And then we know that the this electric field, yeah, dependence of the dv dx, yeah. And then mobility and diffusion, so we have a dependence of the charge, yeah, and then the temperature, and then Boltzmann constant. And then by integration, yeah, to this left and the right, so we can get the this equation. And then we can have a V0. V0 is a contact potential, or equilibrium potential, yeah, or electrostatic potential, yeah. Yeah, this is a is the characteristic, yeah, of the uh, semiconductor. Yeah, silicon have a V0 different with the germanium and with the other gallium arsenide, for example. So then we can get the V0, yeah, as dependence of the finally dependence on the number of dopant of yeah, acceptor and dopant of a donor. Yeah, the number of a donor and the number of acceptor, yeah, to the semiconductor. And then dependence on the uh, number of intrinsic of electron, yeah. So we know that this is equal to P and N, right, at the without impurity. And then of course dependent also to the constant, yeah, of Boltzmann and the temperature. Yeah, different temperature of course will causing the contact potential different, yeah? So the Q is a yeah, charge, yeah, electron charge, or 1.6 times 10 power minus 19 coulomb. Okay, so this is the characteristic of a semiconductor. And we have a example here, yeah. An upright silicon, the PN junction has a acceptor, yeah, number of the acceptor is a 10 power 18, yeah, per cubic centimeter on one side, and another side with the donor impurity with the 5 times 10 power 15 per cubic centimeter. Yeah. So this is the number of a donor and the number of a acceptor. Yeah. Then calculate the Fermi level position at the 300 Kelvin or at room temperature in the P and N regions. Yeah, so we from the equation, so we can have that we have EI minus EF, yeah, so energy potential of intrinsic, and then to the Fermi level after uh, P and N join. Yeah, so we have this electron form. Yeah. So this is a actually, yeah, from the P type. So this is a P type. Yeah, and from the P type, so we can have this electron form. Yeah. So from the intrinsic, yeah, the intrinsic energy at the middle to the uh, uh, Fermi energy, yeah, and the bottom close to the uh, valence band here, yeah. So this is a we have a EI minus EF. This is EF. Yeah. So we have 0.467 electron volt, and then another N type. So we have EF minus EI. Yeah, EF is because of the higher than the EI. The EI is the middle, and EF are close to the conduction band. So then we can have by calculation the number of donor and acceptor. So we have this is the 0.329 electron volt. Yeah, EF minus EI. Yeah. So then we can have the second question, draw equilibrium band diagram for the junction and determine the contact potential V0 from the diagram. Yeah, so then we can see here, yeah, the energy, yeah, energy and equilibrium, yeah, for the junction. Yeah, so this is the actually from EIP as sorry, from the EF, yeah, at P and EF at the N. Yeah, so this is N is close to the conduction band and EF is close to the uh, valence band. So this is the total, yeah, of this energy. Yeah, so this is uh, uh, the energy difference between N and N and P. So or we can move here. Yeah, actually this energy. Yeah, this energy is 0.796 electron volt. Okay. Yeah, actually now we can have a same. Yeah, by calculation. Yeah, by the calculation of KT ln NA ND over square of NI. So we can get the 0.796 as well. Yeah, or by one. Yeah, we can calculate the different. Yeah, the Fermi level. Yeah, of and the N and P, and then we can uh, uh, combination, and then we can get the this energy at the equilibrium state. Okay, so this is the example. Okay, I think we have yeah, I think we end this one. Yeah, for the PN junction. Yeah, and then we can continue for tomorrow or Thursday. Yeah. Tomorrow, yeah. Okay. Any question?
No, Prof.
No,
Okay.
sir.
Jelas ya. So then this is the letter we will go for the yeah, the penetration of electron to the left, yeah, to the p, and then hole to the right in more detail. Yeah. So this is the p-n junction is the basic knowledge for the diode and then transistor. That later we will go in detail. Okay. If you have no any question, I think I will end this class. Yeah, I want to go to Bokoda to Kuala Lumpur. Yeah, for the IIUM. Yeah, for person conducting the project of the my lab. Okay, if you have no any question, so I think I end this class, and then the Assalamualaikum warahmatullahi wabarakatuh.
Thank you.
Thank you,
Thank you, sir.